Hey everyone, it's Dr. Garner here. In this video we're going to look at rates of radioactive decay. So radioactive decay is essentially a random process. So it's impossible to predict exactly when an individual atom will undergo nuclear decay. That said, if you're looking at a large enough sample, the randomness of this process tends to average out, and we can measure decay rates for large samples in this way. And we can define a new quantity that we call the half-life, or the T1 half. This is the time that it takes for half of the atoms in a substance to undergo radioactive decay. So if you have a radioactive sample, the half-life is the time it takes for half of that sample to undergo decay. And we can represent the relationship between the initial amount of a substance that you have and the half-life and the final amount using the equation that I'm showing here. So the final amount of a material that's present is going to equal whatever amount you started with times 1/2 raised to the number of half-lives that have passed. So we can represent this graphically as well. We can graph the percent remaining of an initial sample of radioactive material as a function of the number of half-lives that have passed here on the x-axis. So of course at time 0, you start out with 100% of the material, however much you started with. After one half-life has passed, only half of the material will remain, so 50% will remain. After another half-life has passed, after two half-lives have passed, half of that 50% will remain. So in other words, 25% in total will remain after two half-lives have passed. Same thing after 3, half of the 25% will remain, so we'll have 12.5% remaining. Same thing after 4 half-lives, half of that 12.5% or 6.25% will remain. And you could keep going with this indefinitely. So you're going to asymptotically approach 0% remaining. All right, so let's look at a few problems doing calculations involving half-life. So we have a few of these. Again, I would encourage you to to pause the video and practice this problem on your own first, and then take a look at the solution after you've done that. All right, so in this problem, we're being asked to consider a sample that initially contains 50 grams of a radioactive isotope, and we're asked how much of this isotope will be present after 3 half-lives have passed. Alright, so for this we need to use the equation for half-life that we introduced on the previous slide. We're trying to find the final amount of material that's present, and we're told that the initial amount is 50 grams. So we know that value of 50 grams is our initial amount. We know that the number of half-lives that have passed is 3, so they tell you that 3 half-lives have passed, so we'll put that value in here. So this problem is just a matter of plugging in these two quantities into this equation and solving for the final amount. So the final mass of material I'm going to have is going to equal that initial mass of 50 grams times 0.5, so times a half, raised to the number of half-lives that have passed, so raised to the power of 3 since 3 half-lives have passed. If I start to work out the math here, if I simplify this exponent, I'm going to end up with 50 grams times 0.125. If I work out the math, I'm going to end up with 6.25 grams. So that's going to give me choice B as my answer here. All right, let's take a look at the next problem. In this problem, we're going back to that americium-241 containing smoke detector, and we're told that a typical smoke detector contains about 1/2 of a microgram, so 0.5 micrograms of americium-241. And we're told that the decay of americium-241 has a half-life of 432.2 years. And we're asked how much americium-241 would remain in the smoke detector after 25 years have passed. So again, we would use our equation that relates the final to the initial amount and the amount of half-lives that have passed in order to approach this problem. So if you haven't already done so, go ahead and pause the video and try this one on your own first. All right, let's take a look at this together. So we are trying to find the final amount of americium-241. We're given the initial amount. We're not explicitly told the number of half-lives that have passed. Instead, they give us the half-life time, and they give us the time that has passed. So we need to first figure out how many half-lives have passed. We can do that by dividing the time that's passed, the 25 years, by the time per half-life. So then our units of years are going to cancel out, and we'll know how many half-lives have passed. And this should intuitively make sense. If a half-life is 432 years, and only 25 years have passed, that's a very small percentage of a half-life, so it should be a number smaller than 1 that we get out. And that's what we get. So 0.057844 half-lives have passed. All right, so that's the value that I need to plug into my equation in place of the number of half-lives. So my final mass of material in the smoke detector is going to equal the initial amount of 0.5 micrograms times 0.5 raised to the power of 0.057844, since that's the number of half-lives that have passed. If I simplify this exponent, I'm going to get a value here of about 0.96, and if I work out the math, I'm going to get a value of 0.48 micrograms. So that's going to correspond to choice C here. And it's always a good idea to just kind of take a step back after these problems and ask yourself if your answer makes sense. And it should, right? If only a tiny fraction of one half-life has passed, we would expect for the amount of americium to be pretty similar to the original amount. So 0.5 micrograms is pretty similar to 0.48 micrograms. All right, let's try out one more problem like this. Again, I would encourage you to pause the video and try this out on your own first, and then take a look at the solution. All right, in this problem, we're being told that sulfur-35 is a radioactive isotope that's commonly used in a lot of biological experiments. So if you ever work in a biochemistry lab, this is a really common isotope to encounter. We're told that the half-life of sulfur-35 is 87.5 days. And we're told that a researcher purchases a sample of sulfur-35 that initially has an activity of 25 millicurie. So the little m in front of Ci just represents millicurie, so 1,000th of a curie. And we're asked what the activity of the sample would be after 350 days have passed. All right, so this question is almost identical to the one that we just did. The key difference, however, is just what we're using to measure the amount of the material. In the last two problems, we used grams as a way of measuring the amount of an isotope. In this problem, we're instead using activity, or units of curie, to measure how much isotope we have. So remember earlier we saw that activity is proportional to either the mass or the moles or the number of atoms that are present of an isotope. So we can just use curie as a way of measuring amounts. We can plug these values directly into this equation. All right, so just like we did in that last problem, we need to figure out how many half-lives have passed. We know that the half-life time is 87.5 days, and we know that 350 days have passed, so a few half-lives it seems have passed. So I can figure out how many by taking my time that's passed, 350 days, and dividing it by my half-life time of 87.5 days. My units of days are going to cancel out, and I'm going to end up seeing that 4 half-lives have passed. At this point, all I need to do is plug in to solve for my final activity. So the final activity of the sample is going to equal my initial activity of 25 millicurie times 0.5 raised to the power of 4 since 4 half-lives have passed. If I simplify this exponent, I end up with 0.0625. If I multiply that by 25 millicurie, I end up with 1.6 millicurie. So my answer here is going to be B. Thank you for watching. We'll stop here for this video.